The following video is on finding relative extrema. So let's look at the following function, f of x equals x over x squared plus 9, and we want to find all the relative or local maxes and mins. The first derivative test is going to give us one way of doing this. It says that we first want to find all the critical values of f. That means that everywhere else, f prime of x is either greater than 0 or less than 0. So using the quotient rule, we can find the first derivative of f. And simplifying the numerator, we get negative x squared plus 9 over x squared plus 9 quantity squared. And notice that the fraction will be equal to 0 if and only if the numerator is equal to 0, which happens when x equals plus or minus 3. And the derivative won't exist exactly when the denominator is equal to 0. And notice that that will never happen because x squared is always going to be positive, so the denominator will always be 9, or actually 81 or greater. The next step is to draw a number line and mark where f prime is either positive or negative. So here's my number line. I mark off all of the critical numbers, which in this case were negative 3 and 3, and now I just need to decide whether or not the derivative is positive or negative everywhere in between. So I'm going to pick values in each of the intervals. So the interval from negative infinity to negative 3, the interval from negative 3 to 3, and the interval from 3 to infinity. And I'm going to plug any number I want into from those intervals into the derivative. If f prime is greater than 0, then I'm going to put a little plus sign in the interval, and if f prime is less than 0, I'm going to put a negative in the interval. So here I've just rewritten the simplified version of my derivative, and I'm going to start by plugging in a number that's in the interval from negative infinity to negative 3, so namely the number negative 4. If I plug negative 4 into this, I see that the numerator is going to be a plus 4 plus 3, which is a positive 7, a minus 4 plus 3, which is negative. So the numerator is going to be a positive times a negative, which is negative, and the denominator we know will always be positive because it's being squared. So I'm going to have a plus times a minus over a plus, which is a negative over a positive, which is negative. We don't care exactly what value this is, we just care whether it's positive or negative. So I'm going to put a negative sign in the interval from negative infinity to negative 3. Now I'm going to do the same process, but with a number between negative 3 and 3. My favorite number in that interval is 0. So looking at whether each part is positive or negative again, I get that 0 plus 3 is positive in both of the numerator parentheses, and the denominator we know is always positive. So we have a positive over a positive, which is positive. So above the interval from negative 3 to 3, I plug in a positive. Finally, we want to choose a number that's in the interval from 3 to infinity. And I'm just going to pick my favorite number in that interval, which is 10. If I plug in 10 into my derivative, I see that I'm going to have a negative times a positive in the numerator, and the denominator is always positive again. So we're going to have a negative over a positive, which gives me a negative. So once again, in that interval, I'm going to draw a negative. The next step is to draw the slopes to see where we have relative extrema. So wherever I have a minus over my interval for the number line, I'm going to have a decreasing function. So I'm just going to draw a downward sloping line. Anywhere that I have a plus, I have an increasing function, so I'm going to draw an upward sloping line. So you can see in this interval from negative infinity to negative 3, I've drawn in red a decreasing line. From negative 3 to 3, I have an increasing line, and from 3 onward, I have a decreasing line. Now I can see that I have a relative min at x equals negative 3, and I have a relative max at x equals 3. That's because these are where the valleys and the peaks are in my graph. Let's look at another example. So let's try to find all the relative extrema for the function f of x equals x squared minus 16 raised to the 2/3 power. The first step is to take the derivative, which I do using the chain rule. Now I need to simplify it. So notice that the 2 in the numerator of the 2/3 and the 2x are both going to remain in the numerator because they are not being raised to any negative exponents. However, the 3 in the bottom and the x squared minus 16 to the negative 1/3 are both going to be in the denominator. The x squared minus 16 to the negative 1/3 gets pushed to the denominator because of the negative exponent. So I can rewrite this as 4x, remember that's the 2 times 2x, divided by 3 times x squared minus 16 to the 1/3. Now we want to find our critical numbers. So that's going to happen when the derivative is equal to 0, which remember will only happen if the numerator of the fraction is equal to 0. So that will happen when x equals 0. And we want to see when does the denominator equal 0, which would mean that the derivative does not exist. This happens when 3 times x squared minus 16 to the 1/3 equals 0, which I can then use algebra to come up with the solution that x equals plus or minus 4. So I have 3 critical numbers here, 0 and plus or minus 4. I now draw my number line just like I've been doing, and I mark off on the number line all of my critical values. Now I'm going to rewrite my simplified derivative, and I'm going to pick any number I want in any of these intervals from negative infinity to negative 4, from negative 4 to 0, from 0 to 4, and from 4 to infinity. And using any number I want in those intervals, I'll plug them into the derivative to determine whether the function is increasing or decreasing. So here I've rewritten my derivative. I'm going to plug in first a number in the interval from negative infinity to negative 4. So my favorite number in there is negative 7. When I plug in negative 7, I see that the numerator is going to be a negative number. Remember, I don't care what number it is, I just care whether it's positive or negative. The denominator, on the other hand, 3 is positive, and negative 7 squared is going to be positive. Negative 7 squared will be bigger than 16, so negative 7 squared minus 16 will be positive. And when I raise that to the 1/3 power, I will still get a positive number. So I get a negative in the numerator and a positive times a positive in the denominator, which gives me a negative number. So in the interval from negative infinity to negative 4, I'm going to draw a negative sign. Now I'm going to pick my favorite number in the interval from negative 4 to 0, which is negative 1. Notice that the numerator is still negative because 4 times negative 1 is negative. The denominator, however, 3 remains positive, but negative 1 squared is now less than 16. So negative 1 squared minus 16 is going to be negative. And when I raise a negative to a 1/3 power, I get a negative. So I have negative over positive times negative, which is negative over a negative, or positive. So in the interval from negative 4 to 0, I write a plus sign. Now I'm going to do the same for my favorite number between 0 and 4, which happens to be 1. Notice that the numerator is now positive, and the denominator remains a plus times a minus. So I get a positive over a negative, which gives me a negative. So in the interval from 0 to 4, I write a negative sign. Finally, my favorite number, greater than 4, is 50. So when I plug 50 into my derivative, the numerator is positive and the denominator is positive. So I end up with a positive, and I'm going to write a plus sign in the interval from 4 to infinity. Now over each interval, I'm going to draw whether my function is increasing or decreasing. So if I have a minus sign, I'm going to do a downward sloping line. If I have a plus sign, I'm going to do an upward sloping line. And I can keep going in this way. Notice that this gives me that I have 2 relative mins and 1 relative max. My relative max is at 0, and my relative mins are at plus or minus 4. Sometimes we might ask for the intervals of increase and decrease. What we mean by that are the intervals on which the function is increasing and the intervals on which the function is decreasing. In this case, the intervals of increase are from -4 to 0 and from 4 to infinity, because those are the intervals that I drew my plus sign. My intervals of decrease are from -infinity to -4 and from 0 to 4, because those are the intervals where I drew my minus sign. In general, if x equals c is a critical value of f of x, and c is between b and d, where b and d are not critical values of f, then we say that x equals c is a relative max if f prime of b is greater than 0 and f prime of d is less than 0. In other words, at b, we have that our function is increasing, and at d, we have that our function is decreasing. So notice that that forces c to be a relative max. Similarly, x equals c will be a relative min if f prime of b is less than 0 and f prime of d is greater than 0. So notice that this says that at b, the function is decreasing, and at d, the function is increasing. And so that forces, at x equals c, it forces our function to have a relative min. X equals c is sometimes not a relative extrema. This will happen in any other case. For example, let's find all the relative extrema if f of x equals negative x plus 1 to the third. We start by taking the derivative, which once again we use the chain rule for, and we simplify it to be -3 times x plus 1 quantity squared. The derivative is equal to 0 when x equals -1, and the derivative always exists because it's a polynomial, so we don't have to worry about it not existing. The critical value will be when x is equal to -1, because that's the only critical value that we have. So I'm going to draw x equals -1 on my number line. Notice that x plus 1 quantity squared is always positive, and -3 is always negative. So f prime of x is always negative in this case. So I'm going to draw a negative sign on both sides of the interval from below -1 and above -1. And we see that there is no relative max or relative min in this case. Notice here that the graph of f of x looks like the following, and we see that when x equals -1, we neither have a local max nor a local min, even though the derivative, or the slope of the tangent line, is 0.